Good afternoon, everyone. I hope you got something out of the videos on types of phenomena and resolution. These are two important factors to consider excuse me, when setting up or when working with spatial data models. Yeah, so again, apologies for the inconvenience of canceling lecture in person today, but I'm still definitely not feeling 100%. So I think it was a responsible decision. Feel like things will be fine by Monday. I'm definitely on the upswing. So the plan now is to do in-person lecture on Monday and Wednesday next week so that I don't shortchange anyone on in-person instruction time. And again, you can just join in on Zoom or watch the recording after if you're unable to make it in person. So what I want to do now is just kind of go into an applied example and show you some examples from my own personal work regarding resolution and phenomena types, talk about a few different things, and just kind of build on the short content videos that you all are watching today. So I'll build on this more in depth next week in person. I'm going to go a lot more in depth into data models. So don't worry if it doesn't fully make sense yet. It'll be easier to give a well-rounded explanation in person. But hopefully these videos have at least helped give you a broad overview. So what I'm going to do is just show you some examples of what I do for research and how they or how resolution, scale, different data model types fit into that. I think I showed this on day one, but really quickly, this is just a drone video that I shot of my field site. So my field site is way up in the Northwest Territories. I'll show you exactly where in a moment. But basically, I use this fancy equipment called an eddy covariance station to measure the exchange of greenhouse gases, mainly carbon dioxide and methane, between the land surface and the atmosphere. And the place that I work at, called Fish Island, is composed of this weird stuff called patterned ground, where basically it's this large peatland, but because it's permafrost, the way the soil expands and contracts when it freezes and thaws every year, it creates these cool little wedges or polygons that form, where you end up with slightly different elevations and slightly different plant communities based on this 20 centimeter or so difference in elevation. So just for context, we're down here, or I'm down here in Vancouver. Some of y'all might be elsewhere. And the field site that I work at is way up here in the Northwest Territories. Also, just an aside, if anyone's curious, you can change your base map options in ARC pretty easily. So let's look at some satellite imagery instead. And let's zoom to the field site. So it's way in here. So this is the Mckenzie River Delta. It's the largest river delta in Canada and the second largest river delta in the Arctic. And you'll notice just looking at this, it's much, much greener than the surrounding tundra. And so the dynamics of carbon exchange in this environment are very, very complex. And it's a big question as to how this will progress and evolve with climate change and what kind of potential impacts and feedback loops that might create with future climate forces. And I won't get into the nitty-gritty details because it's quite complicated. But anyway, the town of Inuvik is right down here, and the town of Tuktoyaktuk is right up here. These are the two main communities in the region, along with a smaller one called Aklavik, which is over here. But most of this region is very sparsely populated. And so the field site that I worked at is right here. It's at a place called Fish Island. And so it's about 10 kilometers south of the Arctic Ocean. And you can zoom in, And you can actually see these polygons from space on satellite imagery, just on the Esri base map. And so the actual specific location of my research tower is somewhere around here. So at this site, I did a bunch of drone surveys to get a map of the field site with the end goal of creating some sort of landscape classification so I could delineate between these, they're called polygon rims, polygon centers, and then these collapsed troughs, which are just rims where they've actually started melting and thawing. And so these are actually hotspots for methane emissions. And if climate change causes more permafrost degradation and these rims start to degrade and form more of these, then we might end up with more carbon emissions from the landscape. So I did a series of drone flights where I collected a variety of images from this site. And, you know, just flew around, did a bunch of surveying. And so I was able to stitch all these images together to create a bigger photo called an orthomosaic. And so here's just two examples. So here's two examples of images that I was able to stitch together and create. And so you can see that this Esri base map has, I think, a resolution of like 1 or 2 meters. But the image that I was able to create has a resolution of about 10 centimeters. So you can zoom in and see really high resolution imagery of this field site. Now, the way you figure out the resolution of raster image is if you go to properties and you go to metadata, source, I believe, raster information, it'll tell you the cell size. So actually this image is at 5 centimeter resolution, so a bit higher than needed. But basically, this is a very, very high resolution image, very, very small cell size. You can pick out features in this landscape. You turn this layer off, you look at the base map, this is what you see, right? Quite a bit different. You can see the location of the actual weather station. You can see me and Rick Kettler, a lab tech in the department, sitting there flying the drone, looking at ourselves on the camera. And you can pick out all these different landscape features. One of the cool things about drone imagery is it can be used to monitor landscape change. So this is an image that I collected about 2 months later. And you can see the progression, how the landscape has changed, for instance. And so this is actually a higher quality image. I used a different process to stitch all this together. But basically, so this is an example of a very high resolution raster image, which again was created from digital photographs. So just a whole set of these. I also collected some interesting oblique shots, but those can't be used to stitch together any good imagery. So why am I talking about this? Well, these raster images are useful for a variety of things. And one thing I can do with them is look at the landscape and use it to generate a landscape classification. So this is an example of a vector data set. Now, usually you can tell by just looking at them. One is usually an image, one is a series of points, lines, and or polygons. You can also confirm by just looking at the properties, right? So you go to source, and under this part, you see some different information. For one, with vector data, it's normally represented as a shapefile. So you'll see this .shp tag, whereas with a raster image, if you go to the properties, you will see specifically raster information. Oftentimes they're represented as .tif files. So one indicator is that raster and vector data has different file types. So I just manually created this image by digitizing the boundaries of these landscape features. And so think back to the phenomena video where I talked about discrete and continuous phenomena. This is a bit of a blend. So the categories here are discrete. There's 3 types of categories: a collapsed rim, a rim, or a polygon. So it's discrete number of categories. but it's continuous in space. And furthermore, the distinct boundaries are not particularly well defined. There is some transition, right? So when I talked about how do we draw these boundaries, right? Some of this is just a bit arbitrary, me saying this looks good enough. For the purpose of my analysis, I can get away with certain things. So yeah, this is an example of a vector image. And so while the raster image, we can explicitly look at the resolution by just going here and seeing, oh, this is the cell size. For the raster image, or for the vector data, it's not quite as straightforward. One way that we can get an idea of the resolution of a vector image, like I said in the video, is to find the smallest object that we can resolve with the data. So you can open the attribute table, for instance, and you can look at the area. But this one isn't necessarily straightforward because you see there's only 3 records in here. You notice there's a whole bunch of different polygons in here. So it's a little confusing why this might do this. So let's look at this polygon class, for instance. I click this and it selects all these different ones, right? So I said that vector data can be points, lines, or polygons. But building on that, it can also be multi-points, multi-lines, or multi-polygons. And I'll try to explain more what I mean by that next week. But basically, you can have an agglomeration or a collection of individual polygons that are together represented as one feature. So for instance, an example of that might be that you want to represent the buildings on UBC campus, but you don't need to distinguish between the specific buildings. You just need to know where they are for some analysis. You could create a polygon that's just buildings, and it's all the buildings that aren't distinguished. They're not separate. But it's easy enough to explode these if you use this multi-part to single part tool, which I've done here and done this. So I'll turn that layer off. And if we open this attribute table, we see what this tool does is it just splits all these things apart. And so we can sort by shape area. We can find the largest entity, which is just these rims because it's an interconnected patchwork between. Or we can find the smallest feature, which just happens to be this collapsed trough here, if we zoom to it. So it looks like it's got an area of about 2.8 square meters. So you could say the smallest feature we can resolve is 2.8 meters. Now, that's not to say that the resolution of the vector image is 2.8 meters, or the vector data set, because again, resolution doesn't necessarily mean the same thing. But anyway, that's just an aside. So I really quickly want to show just how you can convert between raster and vector. This is something that you do in lab this week. Yeah, so you convert in lab between a raster image to a polygon. You take this NDVI and you convert it to some polygons. We're going to do the opposite right here, and I'm going to show you how you can convert from polygon to a raster. So I have a model that needs this landscape classification map, but it needs it as a raster image because that's the way the computer best works with this information. So we can convert quite easily. And so I'm just going to do this at a couple different resolutions to show you the impact that raster resolution can make and how it might create some inaccuracies. So we're going to convert by the class value. Now, I talked about the mixed pixel problem and some solutions to that using the cell center and maximum area, combined area, right? So we could play around with these if we wanted to change it. I'm just going to leave it at cell center for now because I'm more interested in the cell resolution. So ARC auto determines what is best based on the data that you present to it. So I think I need to clear my selection really quick. But basically it says, oh, 1.2 is the ideal size. Now it's not coincidental that the smallest feature is 2.8. So it tries to go for something that's a little more or a little less than half the size of the smallest feature. That's a good rule of thumb when converting. You want to make sure that a raster cell resolution is at least or at most half the size of whatever feature you're trying to resolve. So you can run this and you can see what the impact is. So this is the resulting classification map, right? See, it matches the image pretty well. So it matches the underlying vector layer quite well. You see it does create these angular jagged edges, but matches pretty well. It also matches the underlying landscape quite well, right? So matches up pretty well with all this stuff. Let's double the resolution and see what happens. So we can change this resolution to 2.4, which is, we'll say 2. Let's make it larger than the smallest feature. So we'll say 3. Now we run this and see what happens. Now this will not take as long to run because creating a raster with a larger cell size leads to a smaller file, faster processing times. Again, I discussed that as one of the main trade-offs, specifically with raster resolution. So we look at this image and we see that it looks a bit different, right? Compared to what we had when we were at 1.2 meters resolution. Now we can see that most of the features are still resolved, but if you say, look here, this is no longer a continuous feature. We have these weird little disjointed bits. We can also zoom to this small feature and see if it was included. And no, it looks like it was absorbed by that rim class, where again, if we do this at a 1 meter resolution, we should find that it is resolved. And it is, right? So we get this feature when we run at 1 meter resolution. We don't when we run it at 3. Just for even deeper example, let's run it at 10 and see what happens, right? So we'll zoom out to the full extent, run it at 10 meters. And this is the resulting image that we get, which looks very dissimilar from what the facts are on the ground, right? So I'm going through this example just in an attempt to sort of highlight the importance of resolution, thinking through it in terms of your specific application. So for my purposes, the smallest feature that I need to resolve on average is about 2 meters. So 2 meter resolution or 1 meter resolution is very much sufficient. All right, so the example I just gave you was of a very, very large scale analysis, or like a really small area. Remember the large scale, small area, small scale, large area thing that I talked about last week, right? So again, that was an example of like really large scale analysis, looking at, I mean, small spaces. That whole landscape classification map is only 300 meters across, right? So the scale of work that I'm doing in that regard is very large, very, very small areas that I'm looking at. So I just want to give you some other examples of resolution at much, much smaller scales, again, larger areas. So I'm just going to show you 3 different satellite data products. So in lab this week, you're doing some NDVI calculations using Landsat 8 data. Landsat 8 is a satellite that has the resolution of 30 by 30, I believe. Yeah, 30 by 30 meters. So, and you're using Google Earth Engine to download that data. So I'm just going to show you some different options in Google Earth Engine. And I'll talk through a lot about Google Earth Engine through the course because I use this a lot for my own personal work. But this is a MODIS data set. MODIS is another satellite or family of satellites that have been orbiting the Earth since the 80s. They provide a long, continuous record of landscape changes, but their resolution is fairly limited. So this is 500 meter resolution MODIS data, which I've calculated NDVI with, doing a similar process to what you did or what you're going to do in lab. Again, you don't need to understand the code to make it work, and I'm not going to walk you through how I did this, but if anyone's interested, I can show you in office hours or something. But so if you zoom out, you see that it gives a good representation at this small of a scale, right? If you're looking at the full delta, you can see a pretty good image. But if you zoom into the specific point, my field site, the image is not so great, right? So like, it just really doesn't highlight any of the variability. And if you turn the layer off, you see the difference it makes. So one step down in resolution is Landsat 8 data. So again, this is the same area as this one, essentially, or it was when I first ran it. I moved this around, but it's the same area, but this is represented in a 30 by 30 meter grid cell. So look at the difference in quality of the image that you get, right? You can make out all these islands, or all these lakes, they're the blue things. You can make out the fact that like this specific island has, so the light color is lower NDVI, which is, as you'll learn in lab, reflective of less productive vegetation. So the vegetation here is less productive than the vegetation over here. And so again, this is a 30 by 30 meter resolution. So it is suitable for larger scale applications than MODIS is because you can resolve smaller features. You zoom out, you get just as crystal clear of a picture of the delta, but if you're way zoomed out and you're working at a really small scale, maybe you don't need 30 meter resolution because again, the trade-off between resolution and file size means that if you want to download this file for the full delta region, it's going to take up maybe a gigabyte. Whereas if you download this file for the full delta region, it's only going to be a couple megs. One step down from this, we've got Sentinel data. Now, Sentinel is a newer satellite. So Landsat is another family of satellites. This is number 8, but it's been going since the 90s, I think. But again, long-term change, fairly good resolution. Sentinel data. This satellite was launched in 2017, I think. So again, all these images are showing the same time period, although it's averaged over the month of July in 2017. The data looks slightly different for each satellite. But this is 15 meter resolution. So again, you zoom out and you see that at this scale, it provides just as good an image as this one and this one. But the key benefit of this 15 meter resolution is that you can resolve features that are half the size, right? So you zoom in even more, and you can see more fine details here than you can if you zoom in here, right? So like look at the boundaries of this little pond here compared to the 15 meter resolution, right? It's a much crisper image that you get. And again, it's all about what you're trying to do. Think about the trade-offs between file size, processing time, how much bandwidth you need to download things, and all that. So this is just a rough overview of resolution with raster data. Now I'm going to give you a quick example of resolution for vector data. So this is a site called Simply Analytics. In lab this week, you're working with some data that comes from Simply Analytics, but I'm just giving you the data. And so this is a 2-week-long module, so you also have next week to continue working on this lab assignment. But then the following week, we're actually going to get some practice using this interface. So Simply Analytics is basically a large repository of census data. I'll cover what census data is in more detail down the line. But it's a large repository for both Canada and the United States. So it's a useful tool, and this might be quite useful for folks who want to work with census information for their final projects. So census data is stored in vector format. So you can see that we're looking currently at the provinces and territories of Canada in this horrible Mercator projection. And so vector data just represents the boundaries of these polygons. And then it associates various attributes with them. So we can see that we're just looking at the population, for instance. And so just highlights, again, some of the differences between what we mean when we're talking about resolution of raster versus vector data. The resolution of this vector data is not quite as straightforward. But if you're looking at data on the provincial and territorial level, the smallest feature within Canada that one could resolve would be PEI, right? So Prince Edward Island is the smallest of the provinces and territories. So if you've got a shapefile that's got the 11 provinces and 3 territories, then this would be the smallest thing you could find, right? So even though, say, you've got these like little islands out here that are even smaller than that, they are part, like this one is part of Quebec. These little islands are part of New Brunswick. So as far as the GIS is concerned, they're part of the same multi-polygon. Again, I'll try and give a more in-depth and elaborate explanation of what I mean by that next week. But again, this is being resolved at the provincial and territorial level. Now we have different options with census data on how fine a scale of resolution we want to look at, right? So, and I'll go through all the different rankings later, so I'm not going to belabor this point, but for instance, census divisions are smaller than provinces, right? So you can see that these are broken up by like regional districts in BC. I think in Ontario, they're called counties. And so census divisions are like one step down from the provincial level. So they are finer resolution. I don't know off the top of my head what the smallest one of these is, but for instance, you can resolve the city of Toronto in this, where if you look at it at the provincial level, it's just one entity. When you break it down by division, you end up with this finer resolution representation of the data, and each of these has various attributes associated with it. Now, the reason census data is better for vector format is because with raster data, you have one cell value associated with each band of the raster image, and though you can stack multiple bands on top of each other, that really quickly explodes the file size. So you got to make sure that all the data is really pertinent to what you're working on. Vector data stores the spatial information, so that's the boundaries, like the coordinates defining the polygons, and the attribute information separately. And it just uses a unique ID to link these tables. And so you can have as many vector attributes as you want associated with each individual entity, right? So you can show not just the population, but say you wanted to show the household income as well, right? You could do that. There's a variety of different variables on here. And all of these are associated with each of these vector entities, each of these polygons, right? So you want to show the percent of age of the population from 0 to 4. It's easy enough to do. And you can quickly change between things that you want to display. It's not that much effort. So we can get even finer resolution. In Canada, the finest resolution that you can get with census data is the census dissemination area. And so these are like city block level. They have less than 1,000 people living in them. So this is what the census dissemination area information for Toronto looks like. If you go to basic population, you see this, right? Zoom out and fly over to Vancouver real quick, just for a comparison, right? So excuse me. Currently, we're looking at census subdivisions, which in Vancouver is concurrent with the municipal boundaries of the Metro Vancouver. So New West, Burnaby, Vancouver, they're their own census subdivisions, right? You can zoom in, look at dissemination areas instead. So in lab this week, you're working with census dissemination areas and census tracts, right? And so census tracts are a slightly larger resolution. They contain usually no more than 7,000 people or so, but when there's like large new housing development that's built in a census tract, then it will increase the size until the next census when Stats Canada comes and redraws the boundary. So for instance, here, I think this is in the False Creek Flats area. There's been a whole bunch of developments that have come up in an area that was once the census boundaries are drawn to cover like an industrial area and stuff. But now with the development, they're probably going to change the boundaries of this census tract, right? But so this is just to kind of compare and contrast the ideas of resolution between raster and vector data. Again, I'll give a more structured and well-rounded explanation of what this all means and the implications of it next week, but I just wanted to try and give you some applied examples.